So let me tell you what this talk is about. Before that, let me acknowledge my student that is the main author of this project is Lorenzo Gobiello. He finished his PhD with me. He's now a postdoc at MIT Media Labs. And he looks like this. So the talk is on the broad framework of network science. So network science is a field that started theoretically about 10 years ago. The National Research Council circulated this pamphlet that sort of told us, to the more theoretically inclined researcher in engineering, that we should start thinking about developing a theory of massively large networks and the study of networks from first principles for representation of physical, biological, and social phenomena. So what happened then is that there was lots of activity, lots of funding agencies became interested, started funding different projects, and much of the research is focused on the structural properties of networks, namely connectivity, degree distributions, power laws, all these kind of things that were great and kept us busy for about 10 years. But what I think that is now important to recognize is how this network has evolved over time and what are the interesting problems now. So here's a picture from today, and the natural next step is to try to start modeling, in my opinion, agents' interactions. So now we have all these social networks, social media, kids running around and interacting with each other. And there is really the challenge of modeling on top of the complex network the interaction of the human agents. So how can we model that? So in order to attack this problem, the basic premise that I will start with and that we have followed in my research group, a very small research group, me and a couple of students, is that simple local rules of social interaction can explain complex global dynamics. So we take a reductionist approach. So modeling the human behavior in all its facets is complicated and will lead to a model that I probably won't be able to solve. So I will reduce the model and will pretend that humans are governed their actions by very simple rules. Okay, so this is simplistic, but the idea is that very simple rules can trigger complex global dynamics. So this is not a new idea. It has been around for a while, and it is the typical idea that physicists have used for a long time. Whether you have a percolation model, a random graph model, a cellular automaton, or a spin glass system, you always have simple probabilistic interactions, and then you look at global behavior. On top of that, if we use algorithmic models of human behavior, we'll be able to do complexity analysis that is typically absent in these static models, because we want to model the dynamics of interaction. So that's a new thing on top of that. What are the dynamics? And this is, I think, a slide that resonates well with what John has been preaching for many years. Actually, I think I just took it from his talk. Yeah, the talk shows something like this. There are dynamics of the network and dynamics on the network. So what do I mean by that? Dynamics of the network is that the network evolves over time, and time t0, time t1 may become different. Time t2 might become different. Maybe it's an encounter network of people that meet each other, or maybe people meet new people, and so on. And then there are dynamics on the network. That is a dynamic process that occurs on the network that we want to model. So at some point, some node might become active and might exchange information with another node. And then there is another type of interaction at time t equal 2, and so on and so forth. These dynamics for us are governed by humans. All right? So it's not anymore a computer algorithm on which we have control over, but are humans that are doing these dynamic processes. And in the very spirit of Herbert Simon, it was saying that behavioral processes can be reduced. So this is really nonsense. Is that behavioral processes can be reduced to algorithmic processes. So we assume that when a human is is given a series of alternatives, really acts according to an algorithm. We want to model that and discover the network dynamics. Okay. So that's the philosophy of the talk. Okay. So if now is a good time to fall asleep if you don't buy this philosophy. If you are interested by this philosophy, then you can continue listening to the presentation. So based on this philosophy, I will touch on two topics. Topic number one is social computation. Social computation means that I will have a population of complex agents solving a distributed computation task that collectively they want to solve. Think about, if you're a control theorist, think about consensus problem or something like that. And I will, as I said, I will reduce these complex agents to very simple agents that are homogeneous and act according to a simple algorithm. Nevertheless, I would like the simple rules to be able to predict complex global behaviors. Second topic is emotional contagion. So both of these topics are data-driven, but the second one is at much larger scale than the first one. And here what we like to model is instead of exchanging information, maybe the agents exchange opinions and even emotions. So they're able to influence each other emotionally. So you go from a picture where you have just information theory to actually a picture of human behavior. And we study expression from the data set from Facebook, which with whom we collaborated. They gave us access to a huge data set, and we were able to study emotional contagion on their data set. And we want to detect and quantify these effects in the network effects. And then there are two ancillary topics that are really work in progress that I will mention at the end, just a few words to tell you how the work is evolving in the lab. And these are about network epidemics, using a data set from Yelp that is now available. That's pretty cool. And some cute models of segregation. These are theoretical models of segregation that have some open problems that have remained open for many years, and we are trying to do some progress on that. Okay, so this will come at the end and show you what is the current work that we are doing. So let's start with the first topic then, social computation. So for social computation coordination games, we really built up from the work of Michael Kurtz and his collaborators at Penn that started this line of experimental research. So what they did is to try to see how people behave collectively over a network when you try to solve problems. So they had a subject coming in the lab, they arranged them over a network, real people, and they gave them a problem, a task. For example, that can be coloring a graph, it can be consensus, solve a consensus problem, and you can only interact with your neighbors. You don't have a global view of the whole network. Okay, somehow you have to solve the problem and reach an outcome. And there was in their work, there is no attempt to model human behavior, but they concentrated on what kind of network structures facilitate a solution compared to others. So for example, a typical result would be that on one kind of network, it can be easier to reach consensus than on another kind of network, and for coloring, there will be some networks on which humans are more prone to solve the problems, and some networks are harder for humans to solve the problem. Okay? And this work received quite a bit of attention in the context, of crowdsourcing, human computation, and so on. So what we do on top of this, what we want to do is to model the dynamics of the process of how humans converge in their behavior. Okay, so we want also to model the dynamics, not only the network structure. And we focus on two types of games. One is the matching game, in which you want to find pairs of nodes that are connected. So you invite your neighbor, and your neighbor might respond, I accept your invitation, let's make a pair. And you want to have a complete pairing of the graph. And the other one is a group membership game, and I will talk about this second one. It is sort of an evolution of the, you can look at it as a one-to-many matching. I want to talk about this one, is the group matching. And we focus on algorithmic dynamics. So how does the group matching game work? Let me describe it to you. You have two kinds of nodes in the graph. And each person that comes in the lab is assigned a role. You can either be a leader or a follower. So leaders are boxes here, and followers are circles. And they form a bipartite communication network. And each agent has knowledge only of its neighbors, not of the entire network. This means that if I'm leader 1, I know that I have a communication with A, B, and C, and nothing else. And if I am a follower B, I can either join the team of number 1 or join the team of number 2. Okay? The objective is that each leader has to build teams of a certain number of followers, and each follower can join only a team, one team at a time.
There is no communication among the leaders?
There is no communication among the leaders, bipartite. And there is a global objective. So the game is not solved until all the teams are complete. Okay? So there is a willingness of the leader to have global stability. So you want your team to be complete. And the followers are sort of changing between teams to explore the state space. This will be clearer in a moment. So how do we play them? How do we make these people play? So we used a very similar setup than the Kern's group. In fact, we modified their software that were nice enough to share with us. So here's how we do. Each user controls one node through a computer interface. So it comes in a lab, so you are told the rules, and then you have a mouse point-and-click interface that it's shown here. For the case of a follower in this case, so you are a follower here. So what you see here are 3 nodes with an arrow pointing to you, which means that the 3 white nodes are actually leaders that are inviting you to join their team. Okay? The 2 green nodes are 2 leaders that are not doing anything, so they're not asking you to join their team. And currently, you have clicked on this node and you have joined this team. Okay? So these are your options at this point. You are currently joined to this team, and you can also deselect this team and join some other team if you want. And notice that here you are given the time it's running. The time is running, and the game has to be solved by the time it expires. And remember, the common goal is to reach global stability. So what do you do? If time is running, at some point nobody stands up and says, okay, the game is solved, then you think, oh, maybe my choice was not the right one, maybe let me try to explore another state of the game, and maybe I should drop this team and join another team, and maybe we will make progress in that way. And you are given 5 minutes, and if the game is solved, everybody is paid $1. Okay? So you can make money.
There is no global information being given as far as how close you are?
No, not in this experiment.
Just time?
Just time.
When is a team considered to be complete?
When all the constraints are satisfied, which are every team has CL followers.
So CL is a fixed number for each team from the very beginning?
Yes.
Okay.
And as soon as it succeeded.
As soon as it succeeded, the algorithm would say, game is solved, you earned $1, let's go to the next game. If time expires, the window will say, time has expired, you didn't earn money, let's go to the next game. And we played 36 games over 10 networks of 16 nodes each. These may look to you like small numbers. Actually, for the matching game, we played more games. But I can tell you that having this setup is not, I mean, looks easy, but it's just a coordination effort to have the people in, write the protocols, have them sit at the computer, explain what to do. I mean, it's a lot of overhead. So this might look to you like small numbers, but actually they are not. They are not such small numbers. So then we try to come up with a reasonable, very simple algorithm that might model the human behavior. And basically, the algorithm really trades off between the desire of the leader to reach local stability and the desire of the followers to explore the state space. So basically, a leader, what it does is it is not satisfied this constraint, then it will propose new followers to match their team, preferring unmatched followers. So of course, you prefer unmatched followers over matched ones, and send a team join request. And the follower is going to explore the state space, and we do this exploration randomly. So basically, if you have a team join request, then choose one at random and join the corresponding team with some probability. Of course, you can make this probability depend on time and make it faster when time is close to expiring and you have not solved the problem, but we found that this didn't change much. So we make this constant. We found it didn't change much. So basically, these are exploring the state space, and this is trying to find a fixed point. Okay? And so the algorithm has some properties. It's memoryless, uses only local information, is self-stabilizing. It makes progress and it never goes back. It always improves the situation. Exchange only one-bit messages are enough. Leaders pursue local stability, and followers provide the randomization that is needed to explore the state space. So how does it perform? This is a comparison between the algorithm and the experiment when you normalize time so that times are on the same scale. And all this plot shows is that there is a correlation between networks that are perceived as difficult to solve by the algorithm and the networks that are perceived as difficult to solve by humans. So if network is difficult, is here, is difficult for both, and this is easy for both. So it's a reasonable outcome. But more interestingly, perhaps, is this plot. It shows that it seems that this is only for humans. This plot is only for humans. And it seems that here I have two lines. One is stability, so when you solve the network, and here actually these networks were not solved. They were particularly difficult, so you exceeded the time limit. And here they were solved. And here is an approximate solution when only you are epsilon away from the optimum, basically. Just one node, one pair is not met. So it seems that you quickly are able to come very close to the optimal solution, but then it might take a long time to improve it to the optimum. Right? So that's the hypothesis from the experiment. A good solution is always found quickly, but it can take a long time on some particularly difficult networks to improve it to the optimal solution. Okay? Now, the cool thing about having a computational model, a very simple computational model, is that you can do complexity analysis on this. You can throw math at the problem. You can try to prove these kind of things, and in fact, you can write this sort of theorem that says, for any graph you are given, that particular algorithm is going to find a solution that is 1 minus epsilon away from the optimum, so arbitrarily close to the optimum, in a time that is linear, with a pre-constant that depends on epsilon, with high probability. But there exists a family of graphs, a sequence of graphs that are particularly difficult to solve, such that the time to find an optimal solution is exponential. Okay? Optimum, it means that you have solved the all teams have found the right.
So that this is
exactly. So everybody is happy. So all teams are complete.
What do you mean by insignificant graph? Because you're not given a graph.
Well, you know the graph. You are the organizer of the game. So in the beginning, there is a bipartite graph that tells you who is connected to whom. Okay, so I can choose the bipartite graph and give it to the algorithm.
Who knows the graph?
Just me. just the organizer of the game, not the people playing. So if I can find an example of a graph that if I feed in this graph to the algorithm, the time it will take to complete is exponentially the number of nodes. On the left, yeah, the leader is a follower. Yeah. Yeah, these are a family of graphs.
Nobody knows it from place, you know.
I know. Yeah.
So now,
GN of
now I start.
You study
It's random allocate this up. I send a diagram, I get people, and they connect with me. Right? So you go through a sequence of graphs, it's
Yeah.
analytic. And then how does the sequence you generate compare to the original graph?
It's a family of graphs. It's a family of graphs that you have to do a GN that depends on the number of nodes.
But the original
So
graph
how-
also has connection with the original graph, right?
Is it true that the new graph has to be a subset of the old one, in the sense that, you know, the initial
So-
graph that you give limits the possible connections?
Yeah, imagine make a simple example. Imagine a ring of n nodes. So you give a ring it's not possible here because it's not like that. But if you imagine you give a graph of n nodes, and then you give n plus 1, n plus 2, n plus 3, and so on.
No, I understand the graph. Originally you have a diagram, so you have connection within the followers,
Yeah,
which nobody knows.
right.
So now they construct connection within the followers.
You give another game.
Right, but as you go into the game,
Right.
there are partial graphs being constructed,
Yeah.
right? Because not everybody has connection within the followers.
Right.
And you can compare those graphs to the original graph, which one you know.
Yes.
So it's a good, if the game progresses well, if you come close to that graph, or it doesn't matter?
No, if you're progressing well, you come close to the graph. The closer you get, then that's your performance.
But the other thing that Kerr does, right, he controls the information pattern. What do I know and what do you know and who knows what? Did you do anything with that?
No, it's just in the beginning, just the graph.
You don't play any games.
No. That's
The reason that it's important is he finds in the same way as the graph that we've done that change the information pattern on the same game, same number
Oh, yeah,
of people,
yeah.
the results are different.
Yeah.
We call those paradoxes.
Yeah. So of course that's important to know what you call.
That exponential complexity result, there exists a graph, does it depend on the algorithm or it is for any algorithm?
No, it depends. It depends on this particular
Algorithm.
For this particular, in fact, this problem you can solve much better with more complicated algorithms.
What is delta?
Delta is no degree.
The maximum degree?
Yeah, so no degree. Okay, so maybe should I tell you a little bit about how to get this result? It might be.
One question. So in the beginning of the game, I know only my neighbors, right? And I can only send messages to this neighbor. I cannot send messages to anyone else, right?
Sure.
So it's fixed from the very
Yes.
beginning.
Yes.
Okay.
So how do you reason about this? Basically, you can think about this as a Markov chain evolution over one-to-many matchings. In the first state, there is an empty matching. Nobody is matched to anybody. And then the algorithm runs, and at some point, you go into a state where you have one person is matched, one follower is matched, and then you never go back, and you start doing your random walk, your Markov chain at this level, and then at some point, because of the randomization effect that you're exploring the state space, two followers are matched, and so you go to improved state where two followers are matched, and you have your Markov chain evolving here, and so on and so forth, until you get an approximate solution. Okay? And then eventually you run here, and then you get to the optimal solution where everybody is matched. And notice that the arrows that take you from the left to the right are a large number here. They can become less and less. The cardinality of these arrows is less and less as you progress from the right. So it becomes harder and harder to reach the optimum. And so what you need to do in your combinatorial proof is to show an upper bound of the number of steps that you require in this walk to reach a good solution, and the lower bound of the number of steps in the worst case that you need to be able to hit that path that brings you to the optimum. So that's how you reason about this thing. Okay? So that's what we do in the proof. Okay, so that's the results we have here. We have similar results for the matching problem, and this is the summary. So now I can switch to the second topic. Unless you have additional questions on the computational part, we'll go to the emotional contagion.
How did you answer the broader question of you starting from?
The how to model humans. Yes. So again, what we take here is a very crude approach, right? We reduce the human to a very simple algorithm, and we show that with the tools of Markov chain combinatorial analysis, complexity tools to find all the results of the progress of the algorithm, you can actually prove properties of what you observe. So you have predictive power with simple models. So it's a proof of concept that says, despite the strategies, actually we ran surveys after the exit, and people are showing all sorts of ideas that they had when they were running this game. Despite people have very heterogeneous algorithm in their mind, maybe some algorithms are not even explicit because they don't even know what they were doing. Maybe some people are acting randomly. Forget about all of that and come up with a simple model that actually captures the essence. And the essence in this case is the leader wants team and the followers want to explore the state space. If you capture this essence, you are able to prove things that might be difficult to show experimentally because these results are asymptotic, so you would need to scale them up.
But the fact that you don't know anything seems to suggest that you cannot do better than randomization.
In what sense?
Well, you don't know. You said that there are better algorithms, right?
Sure, but these algorithms will
More
more complicated. So we assume that these algorithms,
But
the average human is not going to have a computer to optimize.
would it need to try an algorithm that's just a little more complicated and see if it fits your data better?
Yes, that's true. And also other things that we should put into the picture is that in real life situation you will have more constraints like preferences about teams. You don't completely randomize. Yeah, you have profiles.
But actually, what do you predict here and what do you attempt to verify? You say, I cannot predict what can you predict?
That some networks are more difficult than others, and that on the difficult networks you can actually approximate well. So humans can approximate well the solution.
That you compare with actually what humans do?
Yeah, the plot that I showed you, right?
You compare the actual prediction of the algorithm with what the humans do.
You see,
You collect the data of who they follow and so on and so forth, and you compare.
not at the macroscopic scale, only at the global scale.
Hey.
Only at the global scale, you can
How
see
do you
that
compare
humans.
If you run over 50 networks, you take average, how do you compare?
So over different
I take
networks.
50 students and I put them in the program. I do 50,000 lines.
Per network. You look at each network, what is the performance? You see that for all networks, for each network, you always reach an approximate solution very quickly.
Oh, so
But
the
the
only
only
thing you're trying to predict is whether I'm predicting fast or take a lot of time. Yeah, you try to correlate it with the literary error.
Yes.
That's the property there.
Yeah.
Massimo?
Yeah.
Now, here the communication is one bit communication.
One bit.
Each follower looks at the neighbor. Now, in all these setups, there is interaction among the followers. They talk to each other. Now, does the convergence take place much faster in the presence of interaction?
Yeah, that would be a good question to ask. We didn't explore it, but of course you can introduce, more interaction, more rounds. Leaders might advertise things to make them more interesting to the follower. May give incentives to change their preferences. You can add complexity to the model.
But does the analysis become, the market chain goes away somehow, right? Once you have that.
Yeah, I mean you have to sit down and look at what your model, how to solve your model. Yeah, so this is a very simple, simplistic model. I'm not claiming that we we are modeling the full complexity of the. Okay. So let's go to the second one. That is more of a big data problem. And here is detecting emotional contagion. So what do we want to do here? We want to see if over the network it's possible to exchange emotions. And how do you quantify emotions? So what we do is we look at sub-updates that are also called posts in Facebook that are a way of doing undirected expression on Facebook. So basically you write something about yourself on a particular day that is not directed to anybody in particular, some message that maybe says what you are doing in that moment, how do you feel, these kind of things, and people use that to communicate to their friends their expression. And we analyze those using linguistic analysis. Linguistic interaction word count is a software that is popular in psychology and basically gives a score to different semantic categories that you have. For example, one of them can be happiness, and you get a score of your happiness based on the word count of certain words in post. We count the fraction of post with a word from a given semantic category. In this example,
So you do ugly words and they are a letter and then 3 dots.
yeah, they're classified as nonsense. Yeah.
Because they may be
Right. So here is an example of what you have for different times, and you see that people on a large set of Facebook users are actually happier during holidays, and they're using less negative words during the holidays because they're happy. Just to give you an idea of how this data looks like. And then how do you look for, remember, we want to discover contagion. So we want to discover if I'm happy, can I make my friends happy? So a group at Facebook, in the data science group led by Adam Kramer, came up with a paper that was doing experimental treatment of Facebook users. So basically what they were doing, they have Facebook, they have the power over whatever they do on their program. So they apply some filters to a subset of users, and these people were not allowed to see more than a certain percentage of good words, or some people were not allowed to see a certain percentage of bad words, and then they measure how these people reacted to that. So that you can measure whether there is an effect of being influenced by good words and being influenced by bad words.
Did they know that they were participating?
Did they know that they were participating? Do you think this is a good thing to do? So the editors of the journal accepted paper, it went public, and then
it was a big controversy.
Big controversy. The press went to it and say angry mood manipulation subject. Facebook is is playing with your sentiments, with your emotions. They should not do this. It escalated all the way up to the CTO. That was the guy was almost fired. I don't know if he was almost fired, but anyway, the CTO made a press statement, said we should have done things differently. We apologize. We should have never done this. And he said we should have considered other non-experimental ways to do this research. And actually, they woke up because they discovered that we had a paper before them, and he put a link on the press release that you can click and our paper appears, but I wonder why didn't they use it in their publication, I don't know, but after that they acknowledged that there are other ways. And I'm going to show you the other way that we did. And the idea is that you don't need to do an experimental analysis, but you want to do a non-experimental, non-invasive analysis of this. And to do that, you have to identify an external variable on which you do not have any power. Right? You are not the one who's going to decide whether somebody is going to see more posts that are positive or negative. And once you have this external variable, you have to use it to discover your correlations. So we use only observational data, not running an experiment, and and we use a method called instrumental variable regression, which is based on this variable that we cannot control, but we can observe, and it's sort of a natural experiment, because the variable is not controlled by us. It's given by somebody else, and we want to discover what's going on. And this is a picture, by the way, of my student that is surprising people when he's giving this interview at Wall Street Journal. Live. So he got, Lorenzo got some attention after this. At the end, it was good. So what is the statistical model then that we use? We have the user expression, or its a state of emotion. It's given by a variable that is depends only on time. Maybe people on weekdays are more likely to write about certain things, and weekends about some other things. Then there is a baseline effect, because this person, people have different characters, so some people might use more words of a certain kind, some people might use more words of other kind. This is the external variable, okay, the external variable that is influencing your mood, your semantic expression. And this is the term that you want to estimate. It's the linear combination of all the expressions of your friends. How do they influence you? And you want to discover the parameter, the contagion parameter lambda. And you normalize this by delta I. So if these are 0 ones, namely you are either my friend or not, then this would be the null degree. So in the sense that if you have a large number of friends, you are likely not to look at all of those posts. But Aij are assumed to be non-negative. In our case, are assumed to be 0, 1.
You will have negative.
Because you hate people.
No, I mean, if I have a bad emotion, then my...
No, the parameter of contagion is lambda. Aij indicates whether you're a friend with somebody or not.
Right. So I would look into it, like you said, they're my friends. So whatever I would accept to them, it would be viewed with a different...
Oh, viewed with different... Okay, so even if I tell you, John, you look very good today, then you say, just the idea of me talking to you.
The reason I'm asking is because we look in what we call network sign graphs, and it's not math.
Okay, that's a good point. Yeah, you can do it.
Relation or things like that. And so when they're non-negative, then it's
Right.
important positive sign.
Yeah, that's a good point. We'll be able to look at how things work.
categorical model. This is not a categorical model. In other words, you assume that you have a way of measuring emotion and feelings, right?
Yeah, you actually don't measure. People say you measure emotion and feelings. Really, what you do is just acknowledge that the words of a given semantic category propagate. Then, if you want to associate that with emotion, you have to do one step more and believe that expressing this semantic category is an indication of your emotion.
How do you set on a value like this? What scale?
This one is given by this linguistic word count software that basically gives you a number that is representative. How many words of this semantic category are you using?
It's a fraction.
It's a fraction.
If I had it,
It's very simple, isn't it?
if I get the classification of types, every person has a type. I can translate this. Then to the exactly what is the value or meaning of the word in different words. Depending on the profile, some bad words may have different weight than others.
Very good.
Is that possible?
So this would be basically tuning this one here. You have a better model for your own character and how these weights depend on that. So this model does not take that into account because it just uses posts. But in principle, you could do that because you have data, so you can access the profile of the person, analyze that, and give a weight to that, and have a different, more complicated. So this is, here epsilon is just an error term, a noise term. So what are the problems with the very simple linear statistical model of contagion? First problem is to identify a valid external instrument. That what is this instrument that is going to to affect your mood that you cannot control with your experiment. Second, you need to do some data reduction because the database is huge. And third, you have to identify the causal dependencies that may lead to biased estimates. Why? Because there is a lot of feedback here that can give you a biased estimate. There is an instrument, and the instrument influences your friend's expression. The instrument might also, at the same time, influence your own expression. So first of all, by measuring how your friends are influencing you, this might be a proxy for actually how the instrument is influencing you, and you get wrong results. And also, yourself are back to influencing your friends and so on. So you have to be careful about breaking all these dependencies. So these three problems. Let's look at each one of them in turn. The first problem is, what is the instrumental variable? Any ideas? So the instrumental variable that we used is very simple. So this is the instrumental variable, it's the weather. So weather is very correlated with emotion or with word count. So I'm kind of happy if it's a good day, I'm a little bit more moody when it's a bad day. So we use the weather, and the weather is logged. So you have access to that meteorological data, and we'll use data from the 100 most populous cities. There is a website where you can get that, and you can geolocate users based on their IP addresses. We assume that they're located in a certain city. So that's how the first problem. So we have a variable. Weather I cannot control. So now Wall Street Journal cannot come after me and say you are playing with people. It's the weather. I'm just observing. Data aggregation is another problem. We need to aggregate data to do this because the database is 100 millions of users, billions of friends, period of observation of 1,000 days. It's a lot of data. So we reduce this to 100 observations by averaging over cities. So here are all users in city G, and I normalize by the number of users in city G, and I take these averages. So this is the average emotion of user in city G at time t, if you wish. This is the average emotional influence on user in city G at time t by all of your friends. And this is the average emotional influence on user in city G at time t by the external variable. Okay, when you sum all of that. Notice that here I'm assuming that this beta and lambda, these are the parameters I want to measure. I'm assuming they are constant. So if I figure them out, I can figure them out from the other ones.
I'm sorry, how do you measure the intensity of an emotion here?
By doing this word count. So this software is basically reading the posts, classifying words in the post according to semantic categories, and giving me how many words of this semantic category are used compared to the words in this other semantic category, and it's giving me a score of the semantic category associated with this emotion.
And the effect of memory that things cease to have influence after a certain time because you forget about them. How do you capture those things?
So there is no memory here. We do it day by day.
This is instantaneous, right?
Instantaneous, day by day. Right. So the fraction of posts at a given day on a daily basis.
Third box that you have.
Right.
Aggregation is also done for friends in the city, or it's
Yes, it's done. So this one are all of your friends. These are all of your friends. And then once you compute the inputs of all of your friends, you sum over all cities.
So is that the summation J, is that across the network, or is it across the city?
No. These are all your friends can be outside.
Outside.
Outside. And then you sum over all cities where you are. All right. So then the third problem, dealing with causality, so these feedback things. So notice that my friend emotion is affected by the weather, by this line, and by my weather indirectly through contagion. And my emotion is affected by my weather, so here, this line, and by the cumulative effect of my friend's emotion, who might be experiencing my same weather. Right? So that's the problem. This these lines are problems. And we need to separate effect of weather and effect of contagion to obtain unbiased estimates. Okay? In terms of equations, you can see it here. These I rewrite the average model by putting a bar to write all the summations. So it's the same as before, the same model as before. This is myself. I'm influenced by the weather and by the cumulative effect of my friends here. And my friends are affected by their weather, just what I said before, plus my weather as well. Right? So I want to delete those. I want to put this to 0. If I put this to 0, these two, they don't share the common thing, and I can substitute this into that, break these connections, and get a model by which now I estimate beta 1 and lambda. Okay? So how can I do that? How can I delete these effects? Very simple. Just consider observations for city-day pairs that experience different weather. So you post that in your data set, so you break these correlations, you can do, now instrumental variable regression will work. Okay. So once you do that, you have your model.
When you take the weather out,
You take the weather out. No,
that's the weather.
that's so when I look for the effect when it has rain on my friend, should have not rain on me.
Take the weather out. You took a different weather.
Different weathers. So let's look at the results finally. So we can measure both the direct effect of rain on negative cost and the direct effect of negative, the indirect effect of rain, so the ripple effect on the negative cost. So how to read this is basically for different cities. New York is here, Los Angeles, San Diego is somewhere over here, San Francisco, and so on. So for example, for New York City, if it rains, it generates 1,500 additional negative costs in New York City, and about 600 additional negative costs elsewhere, somewhere that has not rained. Okay. More precisely, let's look at this other graph. These are the estimated parameters, beta and lambda. Beta is the effect on the instrument, and lambda is the contagion effect. For different semantic categories, the top is negative, then there are other semantic categories that the software gives, like anger, sad, and as you go down, they become more positive, like feel, achieve, positive, leisure. Okay? And you see that the beta is about, for example, for negative, is between 1% and 2%. So this means that the average number of negative costs increases by 1% due to rain. And the contagion effect, lambda, is between 1 and 2, meaning that it's 1% additional. So every additional negative cost generates between 1 and 2 negative costs elsewhere in another city where the effect of rain was not present. Okay, that's an important factor. So this results that this shows that there is global emotional sympathy to the social network. Maybe not at the level of Beatlemania in the 60s, but a little effect is present. We tend to mirror the semantic categories of our friends, and each post in a semantic categories causes friends who live elsewhere to make 1 to 2 posts in the same category. That is the result. You can also look at how these results correlate with one another. If you look at them in a matrix, and you put the positive and the negative here of your friends, and the positive to the negative here of the user. And basically that means that they are highly correlated, and blue means they are poorly correlated, and you see that the positive correlates with positive, negative correlates with negative, while positive and negative sort of cancel themselves, which is what we would like to use. Okay. So the summary is that the use of semantic expression spreads. Emotional contagion can be detected in online social networks using observational data. This method is non-invasive and is not non-experimental. So that's a good thing. And the real point here, I think we should make, is that given the massive amount of data that we have, what these social networks enable you to do, this is just one example, emotional computation, but now that you have all this data, even if you look for little effects, if you ask questions that are difficult to answer because the effect is very tiny, by the sheer amount of data, you might be able to see the effect. So even a good instrument might be sufficient for large data sets. On the other hand, what we discussed is before, the computational complex agents will already have quite a bit of interaction. So let me just go to the last two topics that are unfinished and work in progress. So this is just other two topics that we are currently working on. So I will not tell you a lot, but just what we are doing. One is to look at a different data set, and this comes from Yelp. And we use it to predict the prediction of epidemic risk. So Yelp has this beautiful data set that actually now everybody can use. Not only, no, before you needed a relationship with Facebook, but now you can grab it. They call it the engineering challenge or something like that. You can play with it. It's 2 million reviews, 500,000 users, of 77,000 businesses that make reviews of these businesses. And it's a pretty big data set, different cities. And you can just download them. Okay? And ask different questions and try to see what the answers are. And what we do is we try to predict the risk of contagion and epidemic spread on the friendship network. So Yelp also gives you a friendship network that is static compared to the encounter network. So how do we measure risk of contagion in the real encounter network? We use business reviews. We construct a network by assuming that if two people visited the same business on the same day, they might have been in contact. Okay? And we assume that this is the real contact network on which the disease spreads. And then we have a static network that is just your friends. Okay? So how does the epidemic differ on these two networks? This is just one question you could ask. You could ask many other questions. You could ask how these networks are different from one another, what are the properties, and so on. And we look at how are we able to contain and predict epidemic risk using all this stuff. So that's what we are trying to do. The other model, and really this is the end, is this work on residential segregation that was initiated by Thomas Schelling, who is actually an emeritus professor here at Maryland. It's another Nobel Prize that is here. And in the 70s, he proposed a very simple probabilistic dynamical model for residential segregation. And this is really a pen and paper model that you can try to study. And it works as follows. You have a network that is a grid or a torus. And by n, each agent is basically either +1 or -1. So red white, so red and blue. In the selection mechanics of the red and blue. And then there is a neighborhood. So each agent considers the agents within Manhattan distance of W as its neighborhood. Okay? You put one agent on each grid point, and then you decide if you are happy or unhappy based on the percentage of neighbors of the same color. Okay? So there is a parameter that says if there is more than 50%, say, of people like me, I'm happy. And if it's less than 50%, I'm not happy. And if I'm not happy, the dynamical system is I will move elsewhere. I will pay my dot and I switch with somebody. If this switch makes both of us happy. Okay? And you evolve like this. And the interesting thing that Schelling noticed by doing, he actually doing pen and paper, a simulation pen and paper flipping coins, was that even if people are very tolerant, say 50%, you would like a mixed environment around you, you suddenly see clusters appearing of areas that are of the same color. So this is a very simple model that shows that local decisions can have global consequences. So despite the simplicity of the model, it's a very simple dynamical model. This has resisted rigorous analysis for many, many years. there are very few results, and only recently people are making some progress, and theoretical computer science, some papers, physics journals are doing a lot of rigorous analysis. So what my student, I have a new student that is studying, is trying to study this model and predict under what conditions the system evolves into segregated areas, how large the segregated areas can be. This really matters, is a mathematical model. How fast is the segregation process? Can we extend it to more sophisticated settings? Is an interesting exercise and research to do. Unfortunately, the colors are not showing great on the projector, but just to conclude, let me show you an example of simulation. Today, we're not like shelling that we need a pen and paper. We can do massive computational work, so that's what Ahmed did, just to show you. Initially, it's initialized 50%, right? So it's very mixed. And here everybody is pretty tolerant, so everybody would like a mix. Half of their neighbors to be of the same color. Nevertheless, there will be few spots that are unhappy, that are the lighter regions that are unhappy. So we run the simulation. So it starts. You'll see that these segregated areas start to grow, and they are bounded by unhappy people that are driving this process, that are starting to change. And they start growing. I wish the colors would show better. But, at the end, you go into this kind of state where you have segregated areas. Okay, so that's the end of my talk.
We want to show that for every positive value of the fraction, you always will have a neighborhood of a certain size.
So this is what we are trying to do actually, and what we are trying to do is that for every fraction, we are trying to find sufficient conditions for the segregated areas to grow. And actually we have some sufficient conditions. But now what we are trying to prove is that the sufficient conditions always happen. But we are still working on it. So that's exactly what we are thinking about.
And that's assuming that the process runs infinitely
yeah.
long period of time.
Yeah. And then the second question is how fast does it go, right? Because the mixing time can be very long and then it becomes less interesting. Because you can have different phases. And if the mixing time is very long before you reach this state, it's less interesting. So you will also would like to show that the convergence state is fast.
This is a amount of time in the space of configuration.
Not sure.
I mean, each time you don't like what you see in the neighborhood, a little bit like what the approach that you took with the other first part of your proof, right? You go click by click, you have a remarkable chain, right? You go from one state of what things are at a given t, and then you go to plus one.
But your neighborhood overlap, right? So
So let's take a speaker.
questions.